So hi, we're gonna to in today's video we're gonna to just to have a look at the minimum spanning tree. So what is a minimum spanning tree? Let's look at a definition. So a spanning tree is defined as a tree-like subgraph of a connected and indirect graph, which include all the vertices in the original graph. So this just means that we want to find a subset of edges that form a acrylic, which is a no cycle tree that connects all the vertices in the original graph. So for example, we have here where we're having a graph like this, and if we want to find a spanning tree, which is we want to only pick the edges that just connect all the vertices we have here, which is A, B, C, D. So we could either pick this, which able to connect all the vertices or 4 vertices we have, or we could also have something like this that connects all 4 vertices. But notice that we can't actually have another edges here, because if we have an edge here, we actually create a cycle for this entire graph where you can reach from A to B to C to D and back to A. This is actually defined as a cycle. So looking at some property we have for the spanning tree. So the spanning tree property are the number of vertex v in the graph. It's actually the same as the spanning tree. So the spanning tree also contains v vertex. And there is a fixed number of edges in the spanning tree, which equals to 1 less than the total number of vertices, which is E equals to V minus E. So how this property derived, it's not actually a minimum spanning tree property. It's most likely to be a tree property. Back in 2521, where we learned trees, is that we have a root in front of the tree, and then a tree doesn't having a cycle. That's why at most it will have numbers of total of vertex minus 1 edges. There are also proof on why this is true, but you could search on YouTube to see a proof, but this is the property we always assume that a tree has, and also it's a real property. So, and let's just take a sample of what a minimum spanning tree really is. So we're having a graph here where we got in total of 5 vertices, and then we got 1, 2, 3, 4, 5 edges. We know that we can't take all 5 edges all within the graph because it creates a cycle. So we know that the number of edges we could have in the spanning tree, it's actually 4. So what kind of spanning tree we can find? That actually we could find a spanning tree. We could find 5 spanning tree. Here's a little graph, and first we could take something like this, where we have connect all A, B, C, D, E vertex, and we have the minimum cost, not minimum cost. We're not guaranteed that it's the minimum. This is the cost where we have 15 plus 20, which is plus 1 plus 5, it's 41. And here we could try another one. We don't take this one, the 15, we take the other one, which also connect all 5 vertices, and the cost is 20 plus 1 plus 5 plus 10. It is 35 plus 1, so 36. We could also don't add the 20, and we add all other ones, where we got cost 15, 20, 15, 10, 5, 1, which is equals to 31. And yeah, and you can see how this go. We could not take the 1, and then we could also take all of them, and then we found the 5, and the cost of this spanning tree, it's approximate 50, and this one is 46. We could have all sort of spanning tree, but we know that we want to find the minimum spanning tree, so that means we want to pick the minimum cost. So in this case, the minimum spanning tree is actually the graph we have now, the edges connected here. To be a more easy way is that we could find all such graph with 5 edges, which is number of v minus 1 edges, and then just create every single graph and then calculate its the cost and throw it all the costs inside some kind of data structure, and we're able to just pick the minimum cost that have. But with a more complex problem, such as what happened if you got 100,000 of vertices and you got like 10,000 or even 200,000 more edges, and you would like to find all sort of different spanning trees that's inside this graph, you are having to look through every single graph. That's just being not efficient, and you just have it just being too complex in finding it, and it also takes times. And in the real world, when you're trying to do all sort of different combinations, you just waste a lot of money on doing such things, and also time in running. So we want to try to minimize the cost of running such algorithms. We want to minimize the cost of finding such path. And the way minimum spanning tree is, we want to try to minimize the cost. So if we want to try to minimize the cost, there's something we do if we always want to prioritize to taking the edges with the lowest cost possible. So in this idea, it might check you to think of something like the greedy example, where we could have a greedy to try to pick the minimum cost possible in constructing our minimum spanning tree graph. So this is actually underlined in an algorithm which called the prime algorithms, which we're going to look at next. So the prime algorithms, by definition, we're trying to select the minimum cost edge and make sure it is connected to already selected vertex. Okay, at first this might be not easy, hard to may not be clear what it means, but let's do an example, and hopefully after the example you're able to getting more understanding of what this algorithm actually doing. So back to our greedy. So we want to try to minimize the cost edge. So we want to choose first the minimum edges out of the entire graph. So looking at the example edges, we could see that the minimum edge is actually this one with an edge A1. So we have B, C, and connect 1. Let's also write on the side on our selected vertex, where we have B and C, it's selected. So now because we want to make sure it's connected to the already selected vertex, and in the current case is B and C, so we only want to look at the next, we want to pick our next edges from the edges that connect to B and C. So connect to B and C, what we have is, let me just change color, because one thing that connects to B, 20 and 5. Which one is more minimum? Which one is having a least edge wave? It's 5, right? So we will connect this edge, which is connect C, to an edge that's not seen before, and we add the edge D. So, and we add D into selected edges. Now what we have now, it's, we take this, oops, why? Yeah, just draw it back. What we have now, we take this, and then we have to compare the next edges, which is connect D to E. So 10 and 20, we will pick 10 because it's more having a large edge weight, 10 E, and we add E to our selected edges. Now we take this and we compare 15 to 20, and we pick 15 because it's having a less cost, and then we put A here, and let's just go by now you could see that we already find one of the spanning tree we have, but let's just go further so that you get more understanding of how this algorithm actually work in constructing the spanning tree. So if we take a first step, we only got 20 left, which is the only edge wave, so 20 will be the minimum, and we by what we have in our algorithm before, we will select this edge. But notice that when we add this edge into our graph, we're actually going back to a vertex that we haven't selected before. So what that means, when we select an edge, like we connect to another edge that we have seen before, it means that we create a cycle there. And just by looking at the graph without anything, you could see that we're able to go from B to C to C to D to D to E to E to A, and then A to B back again. That's a cycle. That's just literally a cycle, and we wouldn't want that, because in our minimum spanning tree definition is that we want a acrylic tree, which is no cycle. So what we do when we're finding a cycle like this is that we just dump it, we just throw it away, and we're not taking those edge. And by the time you got B minus 1 edges, you find your minimum spanning tree. That's quite clever, right? Just to make sure you understand how this algorithm actually works, let's just go through a more complex example. The graph is actually the same as the previous example. Instead, we add a new vertex F here, and then 3 more edges connect to A, B, and C. And let's just run the prime algorithm once again, and to see how we construct the minimum spanning tree. Just to note that what we have for our prime algorithm is that we want to pick the minimum edgeway that's connecting to all the selected vertex we have now, but initially we want to just choose the minimum edge, right? So let's create a list here called selected vertices. Yeah, and then let's just look at the graph now. Which edges that's having the most minimum edgeway? It's this one, right? B connect to C, say, which have an edge wave of 1. So we add B and C with 1. And then add our vertices in our list, B and C. Next, let's just find all the edge wave that's connect to B and C. So what we have is we have F connect to B, and then F connect to C, and then this edge as well, and we want to find which one is the minimum edge wave. And we have 2, 4, and 5, so the minimum would be 2. And let's just take this edge, which is connect to F, having an edge wave of 2, and then add F to our selected vertex list. Next, we want to also pick. Just a reminder, I forgot to pick one. So we also have A connect to B, which having an edge wave of 20, but since 20 also it's more than 2, 4, and 5, we also just pick the edge F to B, which having a more lower cost there. My problem. What next is we want to find all edges that connect to F as well. So we also adding an edge from A to F that's it's having an edge weight of 5. And just take a side note here, what edge weight we have now is we have 4, 5, 5, and 20. What is the lowest cost? 4, right? So we want to pick this. And then we add it to our graph with 4. But notice how this edge is connected to F and also C, where C also is one of the selected vertices we have pushed to our list before. What does that mean when we reach the vertex that we selected before? That means we're having a cycle, right? We're having C goes to B, B goes to F, and now F also able to go back to C. That means we just create a cycle with adding this extra edge. And if we go back to the definitions of the spanning tree, is that we're having a subset of edges that form an acyclic, and it means that there is no cycle. And this is really important property of a tree or a minimum spanning tree, is that there is no cycle inside the graph. And if there's a cycle there, that means we don't want to add this edge, because if we're adding this edge, it's no longer a minimum spanning tree. So what we do is just we want to discard this edges. We just don't consider it. We don't add it to our current graph, and so that it will not create a cycle. Then what next is what we have. It's 5, 5, and 20, and we want to pick the minimum. Let's say we pick 5, and then we pick this 5, which is D to C, and then we add D to C, and D is a new edges. D is a new vertex, so we add it to our selected vertex list. And it doesn't create a cycle, so let's just keep going. We add the edge that it's connected to D, which is this one, and then it's 10. What it's the minimum? It's another 5, which is A to F. Let's just add A. A is a new vertex, so there's no cycle, and we add A to our select vertex list with an edge weight of 5. And now we can add another edges here. Oops. E to A, and then let's just cross it out because we already selected. And then let's just have 15 also added here. Which one is minimum? 10. So we want to pick this edge, which is connected to E, and we know that E is not a vertex that we have selected before, so there's no cycle. And then let's just continue to go 15, and then 15 connect E to A, but we know that A is already selected before, so it would create a cycle, so we don't want this edge to be added. And what next left? It's 20, which is connected to A to B, which A and B is both seen before, so adding this edge meaning that we will create another cycle inside our current graph, so we won't want to add this edge as well. And after all the edges we've been seeing so far, we actually create a edge weight, a minimum spanning tree here. Just double check with the tree we have. We have 1, 2, 3, 4, 5, 6 vertices. And how many edges we have? Just add here 1, 2, 3, 4, 5. We have 5 edges, which is essentially just equals to number of vertices minus 1. 6 minus 1 equals to 5. And there we have our minimum spanning tree. Hopefully this example make a lot more sense to how the prime algorithm actually work. You might also be thinking about, since we're having a greedy algorithm in always pick the minimum edge weight, but the prime algorithm right now is we only want to consider edge that is connected to our current selected vertex. What if we just choose the minimum edge weight that just respect to the entire graph without consider what vertex we have just been selected? And this ideas actually work. And here comes another algorithm, which is called the Kruskal algorithm, where the idea of Kruskal algorithm is that we just make a list of all the edge costs and choose edges in ascending order. Oops, just spelling ascending order, which means we're just choosing them from lower cost to the highest cost and prioritize all lowest cost edges. But since what we told earlier, minimum spanning tree is all about choosing a tree such that there's no cycle. So we also want to add a check here that if there's an edge we connected and it create a cycle, then we won't want to add this edge. So let's just try an example. Let me just copy this example here. Just give me 1 sec. So this is the example that just we've been looked through previously. So let's just run the Kruskal algorithm real quick. So just go through first thing, let's just go through all the edges that we have in the current graph, and let's make a list of it. So we got we got the lowest is 1, and then 2, 4, 5, 5, and then 10 there, and then a 15 there, and then 20, and just make sure we got all edges. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Yep, we got number of edges equals to 8, and number of vertex equals to 6. And so using this list, we're going to pick the lowest, we want to consider the lowest edge here. So first one, we're going to pick 1, which is connect to B to C. And then next one, we want to connect the 2, which is from F to B. And then the next one, we're going to choose 4. But notice that how this 4 is connected to wait, let me just make this a bit different so that you're able to understand how this actually different from what we had before. Just give me 1 sec. Yeah, so first thing, the lowest one, which is 1. So the lowest, let's pick the first lowest cost edge, which is 1 here. So it's connect to B to C. So let's have B and C connect 1. Next one is 2, which is connected from F to B with edge weight 2. And then the next one we have is 3, which is from A to E. Now let's just connect them together with edge weight of 3. And then the next one is 4, which connect F to C. Notice how if we connect this edge, it actually create a cycle between F, B, and C. So because there's a cycle, so we won't want to add this edge in, so we don't take it into our graph. So the next edges we're gonna consider it's with a 5. So let's just pick this. So we have 5 here, and it doesn't create a cycle. And then let's just pick the next one, which is also 5, and then we have adding a new vertex 5 to D. And then next one we have 10, which is 10 to E, D to E. But notice how this create a cycle in the current graph, as you see, so we wouldn't want to add this edge into our graph. And the last one, we got 20 connects A to B, which also create a cycle, if you see here, where it's going from A to B to F to D. So we want to add this edges, so we remove this. And what we have now, this one, it's our minimum spanning tree, where there is no cycle and it's connecting to all vertices we have. And then number of edges here is 1, 2, 3, 4, 5, which is number of edges we have, it's 5, which is equals to 6 minus 1, where 6 is the number of vertex we have in this example. And now what's the minimum cost here? It's 1 plus 5 plus 2, 1 plus 5 plus 2, 10, 5, 15, 16, and it's the lowest minimum cost we have. Yep, and this is all for this video about minimum spanning tree, as we looked at the prime example, as we looked at the prime algorithm and Kruskal algorithm. Just a real quick reminder of what an actual and minimum spanning tree is that we want to pick the minimum edges wave, and that's able to connect all the vertex that it's in the original graph, and making sure that there's no cycle inside any of them. And hopefully this video make a lot more sense to how we're able to construct a minimum spanning tree. And yep, I'll see you next time.